Miles found out, devised a whole process to generate probably a lot of simulations just to try to see if if it was possible to sue actually people for increasing the risk of extreme events. Okay, so there was an outcome. So Miles Allen and Peter Stott and others actually devised the first prototype of extreme event attribution, and I will come back to this later. Okay, so that's one of the challenges, the attribution. There's the challenge of understanding the physical mechanisms that lead to extreme events, so that could lead us to forecast or predict the extreme events. So that's a very useful challenge, or a very important challenge. And now there are even newer challenges that emerged very recently in the past few years. So that's not the past decade, but the past few years, which is the analysis of unprecedented events. So the events for which we don't have statistics. Something happens, but we've never seen it before. So that's unprecedented events. And there are technical challenges of clusters of events or compound events. So there are these events that combine each other or come one after the other, and have the statistics of those events increase. So clusters of extreme define a new event, which is the cluster itself, which is an important feature to analyze. But I will stick to the first thing for the moment. Okay, so okay, so let's go to extreme event attribution, EEA. So in principle, this is a very simple endeavor. So it's the formulation of this actually could be one of those bullet points. So we want to estimate probabilities. So we want to estimate the change of probability distribution of exceeding an observation between two worlds. Okay, we have an observation which we consider that is extreme. We want to estimate the probability of exceeding this observation or a given threshold, because this observation is supposed to exceed a threshold that we consider that is important. And we consider two worlds. One, which we are going to call factual. Factual is a world in which we live with all four things. So human forcings and natural forcings, and a counterfactual world, which is a world in which we don't live, obviously, in which we remove one or two forcings. Let's say we remove human activities. So we are going to compare the probability in two worlds. Okay, and I will explain how we do this. And there is another way of doing extreme event attribution, which is to identify causes of extremes. And some people wonder if an event could have occurred with a similar intensity without identified forcings. Okay, so corollary of this is we can estimate how intense would an event that we observed, how intense it would be in a climate change scenario. So that means that we have identified causes for the event. Okay, I don't know why. Okay. Okay, so those are apparently simple questions, but if we want to tackle them, actually, we have to do complicated things, or things that require a lot of methodological developments, a lot of data. So the first thing is to characterize the event. Okay, by characterization, I mean physical characterization. So how large are we considering? What's the geographical extent we are considering? What's the duration? So are we considering an extreme event that hits one city, or a small region, or a whole country, or a whole hemisphere? So that's an important issue. If you consider what happened this summer, so the major heat wave and the forest fires in Western Canada and US. So that's one event, so that's a fairly large thing. If you consider the floods in Belgium and Germany at the same time, that's more, the extent is much shorter, and the duration was just a few hours or one day, while the heat wave in Western US were considering a few weeks. So that's a different extent, different duration. But if you look at the Northern Hemisphere meteorology, actually, this could be only one event, which is a wave that creates both events at the same time. So the point of view might really be different on the focus you're considering. And then what climate variable do you want to consider? This is a very important issue too. If you just look at heat waves, what killed people in 2003 was not the maximum temperature of the day. Okay, so a few places reached 40 degrees Celsius or exceeded 40 degrees Celsius during midday, but actually that was not the cause of the death of 15,000 people. The cause of the death was the minimum temperature of the day, because in some places the minimum temperature did not go below 30 degrees, and that's really what killed people, not the 40 degrees in the middle of the day, but the 30 degrees during night. And if you look at those two variables, so nighttime temperature and minimum temperature and maximum temperature, those are physically different variables. So they are both expressed in terms of degrees, Kelvin or Celsius or whatever. But if you write down the equation that govern day temperature and night temperature, they are not the same. Okay, because during night you suppress one of the terms, which is due to the solar irradiation. So the equation is not the same. So it's not the same variable, although we call it temperature and we measure it in Kelvin. Okay, it's the same for precipitation. So are we considering, so if we go back to the floods in Belgium and Germany in June, are we considering average precipitation over one day, or the average precipitation, the maximum temperature over 1 hour during a day? So the probability distribution of those two quantities, which are expressed in millimeters or kilograms per square meter per second, for instance. So they have the same units, but they have completely different properties, okay, due to the meteorology itself. So this is the variable you're considering is a very important choice. And this is only guided by the physical intuition or expert knowledge in meteorology. It's not a question of statistics here. Now, we can consider also the link with the atmospheric circulation, which we can call broadly meteorological conditions, but there are other types of variables that can be considered. So those are large-scale drivers that have to be considered too. And again, we need expert knowledge on meteorology or atmospheric sciences to do this. And then the last issue, which is very important, is how are the ingredients of extreme events altered by climate change? Okay, so if most of extreme events are driven by the atmospheric circulation, how does the atmospheric circulation change with climate change? And this is a very hard issue. Okay, so those are issues, scientific issues or questions to try to perform extreme event attribution. But then if we can do this, if we can find methodologies to do this, we need some input, of course. So there are necessary components. Okay, so we need models, okay, which can be physical or statistical models for the variables we consider. So if we have models, we need to validate them. So that's the first issue, and I will go back to this later. And then we need to simulate models. We need large ensembles of simulations because we want to estimate probabilities. So we need models that we can run a lot of times. So we need large samples of model simulations. Okay, and this might not come for free. So we have to think about doing this. We need statistical methods. Why do we need the particular specific statistical methods? It's because we are looking at small probabilities. Okay, so the numbers, so the probabilities, so the probability of having a heat wave like 2003 is less than 1 over 10 to the 3. So that's a millennial heat wave. So we are talking about very small numbers, and we want to talk about changes in small numbers. So that's the main statistical challenge. The statistical challenge is to estimate small numbers and estimate and determine how small numbers change. And the last point, which is a bit provocative, is observations. In principle, we need observations, of course, because we need to describe an extreme event. We need to know what we're talking about. But is this really so necessary? Because I will, there was an example. So I gave an example of the heat wave in 2019 in France. And it turns out that an attribution of that event was done before the heat wave occurred. So I remember very clearly, so that there was a meeting in Toulouse about statistical climatology, the IMSC in Toulouse, and that was it was really hot in Toulouse that week, but it was getting hotter and hotter. And actually, Robert Votard, and the people in Météo France and the Met Office looked at forecast of the heat wave and could do the attribution exercise on the forecast of the heat wave 1 week before it occurred. So when the heat wave occurred, they had the figures in hand to communicate on those. So the observation of the heat wave itself was marginally useful because the forecast was used to do the exercise. Of course, if you do this, you have you open the door for a lot of mistakes, and the more you communicate your mistakes, the less credible you become, and then people won't listen to you. So that's why I put a question mark here. So in principle, you don't need an event to have occurred to do an attribution, especially if you want to communicate about the attribution of an event that you think is going to come. There might be a communication issue if you want to do this before the others. So there's some coordination to be done.
Pascal?
Yes?
You have about 12 minutes yet so far.
Okay, so I'm way behind. Okay, so I will try to go faster. Okay, so I discussed this, sorry, so this is written to, so we want to estimate the probability of an extreme event, so the probability of a climate variable that exceeding a threshold. And we are going to do this in 2 words. Okay, and actually there are 2 things we can do. So we can estimate those 2 probabilities that I will call P1 and P0. Okay, so which are idealized by those 2 probability distribution functions. So let's say that P0 is the probability of exceeding this threshold in a counterfactual world, so it's a small probability, and P1 would be the probability of exceeding the same threshold, but in another world, so in another distribution. So P1 is the world in which we live, and we are going to be interested in the ratio between P1 and P0. And P0 and P1 can be small. Okay, we can also be interested in the, so if we fix a probability, let's say the probability of exceeding a threshold in our world, which is still P1, we can define the same probability in a counterfactual world. So because P1 is a quantile, we can look at the quantile value in a counterfactual world and determine the change of intensity. So those are two equivalent exercises. Okay, so now I will just give one example because I have only 12 minutes. So the example is, well, canonical example for a lot of people who live in the UK, which was the winter of 2013-2014, for which there were major floods in the southern UK. So that's in Oxford, so that's near that place. So there were records of precipitation. And the question we wanted to answer was this one: did anthropogenic forcing affect the risk of having floods like this in the UK? And actually, there were records of precipitation in France, northwestern France too. Okay, so what we did, we used the tool that was devised. So the tool is actually like a factory. It's a huge thing, devised by Miles Allen and Peter Stott at the Met Office, which is a citizen science project called Weather at Home, which consists of a global model, which is the Hadley Center atmospheric model, and which is nested. In which the Hadley Center regional model, so HAD RM3P, is nested. So the regional model is run on a much smaller window, which is roughly that thing. So which has a much better resolution. Okay, and with this approach, we, well, when I say we, it's our colleagues in Oxford and the Met Office, the task was to compare two ensembles of simulation. There was one first set of one ensemble, which was called factual or actual, which contained natural forcings, so volcanoes, solar activity and everything, and human activities, so greenhouse gas content in the atmosphere. So that's the red simulations, okay? And they produced something like 10,000 of model simulations of roughly 1 year. So they start in November and they go through the whole winter, and they slightly change the initial conditions. Okay, so that's 10,000 factual simulations. And then there are counterfactual simulations, so a world that might have been, but without human activities, just with natural forcings. And then since most of the uncertainty in counterfactual simulations comes from the state of the ocean, so they took different initializations of the state of the ocean from the CMIP5 archive, and they produced 50,000 climate model simulations with different states of the ocean. Okay, so I mentioned the fact that it was necessary to validate the model. And if we look at the zonal wind at 200 hectopascal in January 2014, so that's the ERA interim reanalysis with a very zonal flow that you can see here. And those are examples of factual simulations. So the circulation, of course, all the simulations are different, but that's one of them. And a lot of them had at least this zonal feature from Eastern Canada to Europe, which is like this one. So since we are going to look at a small region, which is this one, this was deemed to be satisfactory. And in this counterfactual simulation, of course, sometimes there is no zonal circulation. Sometimes there is zonal circulation, sometimes not. So let's go to the result. So we compute precipitation over southern UK. And then you might be familiar with this type of diagram. So this is a return period, a return time diagram. And we compute the return level of January mean precipitation for all factual simulations. So that's the red dots here, which look like a line, but they are dots, so they're here. And for all the natural simulations, okay, so they are the blue dots, and the average of all blue dots are the dots here. And it turns out that the red line is above the blue line. So which means that we can compute probabilities. Okay, and that was a paper published in 5 years ago, and we wanted to compute this quantity, the fraction of attributable risk, which is linked to the ratio of probabilities that I mentioned, and we found that there was an increase of 40% of the risk of having such an event in the real world, compared to a world without human activities. So that was a major reason. And well, the uncertainty is fairly large, but the confidence interval is positive.
Pascal, less than 5 minutes now.
Okay, so we can give explanations for this, and I will jump to conclusions. We did this a few years ago because our lab contributed to this in the analysis of those simulations. One of the questions we asked was, can we do this without weather at home? Because this is a very heavy computational exercise. The answer is yes. Actually, we devised a statistical modeling approach to do this. I might show an example for this. And then there were other questions that we tried to answer. So there were more technical challenges, but they were interesting because it took us quite a few months to produce those analyses. And can this be done in less than 3 weeks? And actually, this can be done. And after the storms, the winter storms in 2007, our colleagues, Robert Votard and people in Météo France in the Met Office, could produce a paper that was submitted in 3 weeks after the event occurred. And actually, this is done almost routinely now. And now, so this is feasible. Can we go even further? Can we increase the challenge? Can this be done in less than 3 days? Okay, and actually, yes. So there are examples of this. This year, quite a few of the events that occurred this summer actually could be analyzed with the graphs produced and a report that was produced in a very short amount of time. And can this be done before the event arrives? I gave an example for this, so this is possible. I will. So this is an example of what can be done without weather at home. So this is what we did with stochastic weather generator. So actually, we can come up with very similar results just with simulating random stochastic weather generators. But since time is going, I will not go into the details. I was going to speak about other case studies like the heat wave in 2018 that struck Scandinavia, but to some extent northern France, Germany, and Belgium, and the Netherlands. But the type of result is the same. So there's we multiply by 100 the probability of having such heat waves in the future. So in less than 3 days. So that's what our colleagues did. And I just want to emphasize this website of the World Weather Attribution, for which many people, many groups, including Météo France, IPSL, that's the Met Office, and people in the US, who created the World Weather Attribution website, where they produced case studies for extreme events. So there you'll see that there are a lot of attribution exercises for what happened during the previous summer. Okay, so this is in French, but this is to explain that we can do things in advance. So we've produced a lot of those small documents that explain what are the various types of extreme events. So this is a preparation of extreme event attribution for stakeholders. So we communicate a lot about with stakeholders. We produce those fact sheets about generic extreme events, which make things very much easier when we want to focus on specific extreme events, because they contain, those fact sheets contain all the elements that we use to do the extreme event attribution. Okay, so I will conclude here. So there are two types of document that are available on the web that you can find to know more about extreme event attribution. There was a report of the US Academy of Sciences that came out in 2018, I think. So most of the work was done in 2017. So this book actually explains the difficulties, the challenges of extreme weather, extreme event attribution, the types of tools that can be used for attribution. And there are the BAMS, the Bulletin of the American Meteorological Society, publishes a yearly report on extremes that occurred during the previous year. So everybody is welcome to focus on an extreme and publish a short type of paper to analyze the extreme event and do the attribution. So those special issues were created in 2011, if my memory. So there have been 10 so far. The size increases because more and more events are analyzed, and more teams participate to those analyses. But it gives a very good idea of things to be analyzed. And if you want to know more, this is a good way to start. I will stop here, and thank you for your attention, and take questions. Thank you.
Okay, thanks a lot, Pascal, for this very interesting and comprehensive presentation. So we have at least 4 questions in the chat. I hope we will have more, but you will ask them directly using the microphone, and please using an exclamation mark in the chat. Maybe we can start with some of the questions already asked in the chat. Also, some of them may have been partly addressed. So Nicolas, first, would you like to add, you had 2 questions, one's about clarification and one that has been probably partly addressed. Would you like to take the floor?
Yes. Thanks. So yeah, basically the first question I think has clearly and well answered by you, Pascal. So it was like, if it's like a scientific question, to ask if a specific extreme event is more probable due to climate change. So I think the question was on the one graph that you showed over the case study of precipitation in 2013-14 winter in southern England, where you showed like a couple of blue lines corresponding to the counterfactual word. And I just wanted to be sure that I correctly understand this image, because you were talking about some 40,000 simulations that have been done. So I suppose that those blue lines represent an actual small subset of all those simulations. Or am I, is this correct?
Yeah, so thank you for the question. So sorry, I went really fast over this. Okay, so there were actually 11 types of ocean initialization. Okay, because they considered 11 CMIP5 different CMIP5 models to initialize the state of the ocean. So that's why there are 11, I think, 11 lines, blue lines, 1, 2, 3, with dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, so something like 11. So, and so, well, they didn't do a fit, a GeV fit, but so each line like is for a given CMIP5 model for the ocean. So the atmospheric model is the Hadley Center, but the ocean is from a CMIP5 initialization. So that's why there are 11 lines here. But if you do the average, you get the thick line, the thick blue line here. Okay, so there is a line here which is a blue line which is very close to the red line, which corresponds to an ocean initialization which is probably very warm, while the others are cooler. Okay, so there's an uncertainty on the ocean initialization.
Okay, but if I understood correctly, and there's just a sample of 11 members of this somewhat like Monte Carlo simulation.
No, it's not 11. Sorry, it's not 11 members. When I take one initialization of the ocean, I get 10,000 simulations.
Okay, great. Then this
okay, so that's so in principle there should have been 100,000 simulations, but a lot there were quite a few problems, computer problems, so that was reduced to 50,000 sets of data, but that they corresponds to 11 types of ocean simulations.
Okay, thanks. Maybe we move to the next question by Emmanuel. Emmanuel, do you need more clarification about what could be another interesting scientific questions about attribution?
No, not at all. It was answered also in slide 12, I think. So yeah, all good. Okay. Thanks a lot.
Okay, so maybe Shraddha, an interesting question about the need of observations.
Yeah, it is mainly based on the comment made by Pascal on the necessary components. Yeah, I mean, are observations really that necessary? And the example you gave about, I suppose, about the heat wave you were talking, which could be like foreseen even from the forecast data directly. But then even for forecasting, we need like initial conditions which will rely on observations. So I was just like wondering how far the statement was valid.
Yeah, that was really meant to be provocative. So by observations, of course, we need observations just to constrain models. So that's a very important point. But we don't need observations of the event itself.
Okay.
So that's the trick.
Okay.
So
yeah.
That's almost a play on words. So I'm sorry about this.
Yeah. It's okay.
Ricardo, maybe now?
Yes, so first, thank you very much for the presentation. It was very clear and interesting. And I have kind of a question about a definition, which is of this counterfactual world, no? Because I see actually two possible counterfactual world. One that no human activity was ever present, and one where we disappear. Like the first one, I see it's like a kind of a negative feedback, because it's more like whose fault it is, no, of this extreme. Now to assign, say, okay, it's human fault. But the second one could be more motivational, in the sense that, so guys, we had an impact on nature, and nature reacted as well, no, because it reacted for our activities. Like last year in Switzerland, there was this over-pollination, no, that occurred because this pollution kind of lowered a lot, no, human. So we don't really know how the nature would react to our activities, and could motivate to, like, okay, if we stop, what happens, you know? So which kind of counter world we are talking about? And
yeah, the counter world, actually there's not one counterfactual world, okay? Simply because there's a continuum, there's an infinity of counterfactual. But there's only one world in which we live. So we are going to call this factual world, because we have facts. We can only estimate or make assumptions of what a counterfactual world means. And the option is just we don't, well, the options are not to claim that, to claim liability. So a counterfactual world could be a world, let's say, without volcanoes, okay, or a world without the ocean. So we just remove one component of the world, but when we remove it, of course, there are interactions that could be modified. So, but this is done rather brutally. Especially in the weather at home simulations, counterfactual world could be the world at the beginning of the 20th century. So we could let's say compare the 5 decades, the 5 first decades of the 20th century and the world at the beginning of the 21st century. So here it's a question of definition, where we are considered, so there were human activities at the beginning of the 20th century, but not as much CO2 in the atmosphere. Okay, so when you're mentioning the COVID crisis, where last year during almost 2 weeks there were no planes, virtually no cars in the streets. So that could be a real life experiment for short-term environmental modeling experiments. So we can consider that well, there is a world that we know, which is the world of, let's say, 2 years ago, and the world during which the lockdown was almost general in Europe, and see how it affects air quality. So that would be an experiment like this. But we would have to do a lot of experiments, because the air quality in Europe was also connected with the atmospheric circulation and the large-scale atmospheric circulation. And there were very specific features, especially in the spring last year, with the blocking events, and there was no such blocking in the spring this year. So we would have to evaluate the interaction between air quality and the type of atmospheric circulation on, on everyday life. So, but that's yeah, that's a good point. But the interactions, we just suppress either brutally when forcing, or look at a different period of time in which things are at equilibrium. So there are lots of choices. There's an infinite number of counterfactuals.
Before we take the question by Amal, I just would like to complement the response to Ricardo. Maybe Ricardo, you could be interested to look at the latest IPCC report, because one of the key findings is that if we stop our greenhouse gases emissions, we stop global warming immediately. And it's not perfectly intuitive because, of course, we are still not at radiative equilibrium, but the carbon cycle is also not at equilibrium. And so there are compensation effects so that, in fact, when we stop the emission, we stop global warming, more or less. But maybe we can move to Amal's questions. Amal?
Yeah, thanks, Hervé. Can you hear me?
Yes.
Okay, fine. Thank you, Pascal, for the presentation. So I rather have a very general question, nothing to do with the scientific facts that you taught today. So there are a lot of extremes happening in the world, and they all vary with different spatial and temporal scales, and like the tornadoes to the large scale droughts happening. And some of them have been more emphasized in the scientific community. For example, like the extreme precipitation in UK or the heat waves in Australia. And there are also some extreme events or the individual or the like local events which are in line with the expected consequences of human interferences, which are not being studied. So do you think there is a selection bias in the community, in the scientific community, in studying these extreme events and attributing them to climate change? So how do you comment on this?
Yeah, that's a good point. My answer would be yes and no. So if you just look at the BAMS issues, the first BAMS issues were focused on what volunteers were ready to look at. Okay, so there was a cognitive bias on this, and that's, I didn't mention this, but there's a necessity to be exhaustive in the extreme event attribution, just not to prevent these biases. So that's why I strongly advocate the development of methods like the ones I alluded to, but I didn't show what they were about because it would take too long, which allow for more systematic exercises. But yeah, it just takes time and efforts to do this systematically. So people, in most cases, people take examples and use what they know, what the methodologies that they do to do a case study. But this should be much more generalized, and this is what the World Weather Attribution does, or at least tries to do. So this might not lead to peer-reviewed papers, but at least it's more exhaustive. Now, this being said, even if we are not exhaustive, and we as a community, because I no longer do this systematically. I develop methods. I'm not good at applying systematically all methods I know to everything that comes to hand. So that's why we try to we developed methodologies, but we try to disseminate them to weather services, national or international weather services, and who would have the person power to apply them and do this more systematically. Okay, so that's one point. The other point is that in the BAMS papers, actually, we had the option, we decided to opt to publish even papers for which the attribution is negative. So that it's negative when P0 equals P1. Okay, when there is no change, just to avoid speaking of only positive cases. And that was the case, because it comes to my memory. So there was a major flood in in Thailand in 2012, I think, maybe 2013. And our colleagues at the KNMI did an attribution study for this, and they found out that this flood was this flood probability was not connected with climate change. So maybe it caused more damage than was expected, but the damage was due to a poor river management rather than climate issues. So there was this deliberate choice to have papers that could conclude to a non-attribution, so that we can really make statistics about extremes that can be attributed and extremes that cannot be attributed. So that's a step towards also a more general statement about the attributability of events.
Pascal? So it's 3:05. There are 3 more questions, at least, in the chat. Do you have time to address them briefly?
Yes, sure.
Okay, and maybe we will stop there after those 3 questions. And if you have more questions, please do not hesitate maybe to contact Pascal directly, if Pascal agrees, by email, for instance. But so we have a question by Miriam.
Maybe I can give the floor to the others. I can ask Pascal directly in the lab. Just I was wondering, as Ricardo, about the definition of the counterfactual. So if I well understand, so that means that each time it depends on the events to choose which impact to, like the human or the natural impacts to move or to keep. I don't know if it is right what I have understood or not.
But the choice of the event, the factual or counterfactual world don't depend on the choice of the event itself. So the choice is made because we are interested in the event. That's or we know that we can do something about it. But the factual and counterfactual worlds, or the simulations, would be the same. I could look at. I gave an example about precipitation in the UK in 2013-2014, but I could have looked at temperature or anything else. And actually, I also looked at the atmospheric circulation, and there was an extreme in atmospheric circulation in that it was a zonal circulation for almost all of the month of January, which is extreme in itself, independently of the precipitation.
Zinia, sorry if I do not pronounce correctly your name. Would
Hi.
you? Yeah.
Yeah. Thank you, Pascal. The talk is very nice. I have a very basic question. Could you go back to the slide 17? Yes. May I ask that we know that if you select the region, for example, France, it contains several grades, not only one grade. But if you get this curve, this is only one curve for this region. And so my question is that, do you do some pre-processed of your data to obtain this only one curve? Because I think that the different grade, even though the region is not very large, but still their climatology can be different. So I think that if you feed a probability distribution, their distribution can be different. And if you get this return period and this precipitation return level curve, and how do you finally only have this one curve? And this is my first question, and I will ask my second after you answer this.
Okay, so this precipitation, the precipitation.
Sorry, but I want to remark that Niklas has a question he's been on the line for a long time. So maybe I move one question and then Niklas and then, okay.
Okay. The last one from Niklas, please.
Okay, so actually, this is average this was average precipitation over January, and over that region. Okay, so the regional climate model that was used has a horizontal resolution of roughly 10 kilometers. Okay, so there are quite a lot of grid points. So that's the average of precipitation over that region. So there are quite a few grid points here. So we are looking, those were not convective precipitation, so there were laminar precipitation. So it rained everywhere at the same time here.
Mm-hmm. Yes, okay. So it means that you first do the spatial average, and also you calculate the average of the whole January.
Yes.
Of the precipitation. Okay, yeah, thank you. Or maybe Nicholas ask, and then I will ask my second question. If there is still time.
Maybe Pedro, please, Pedro, go ahead.
Yes, thank you, Pascal, for the talk. A very general question. So you mentioned that when the climate change drives changes in general circulation, right, or local circulation, but when it's difficult to do the studies or attribution of these changes in circulation due to climate change, and therefore their effects on the extreme events. So what would you say that's one of the main problems that we encounter when we try to investigate these changes?
The main problem actually was stated by Ted Shepard a few years ago, is that the representation of the atmospheric circulation in climate models is quite uncertain. So that's why we need to resort to well, the Atlas Center is considered to be one of the very good climate models to represent the atmospheric circulation, but some other climate models might not be as good for this type of exercise. So the feature of the present day atmospheric circulation are very important. It's very important to be able to reproduce them. Then the response of the general atmospheric circulation to climate change actually is subject to a lot of debates. So that's why it's very important to have a large sample of models, because it might be very model dependent. So this analysis was done with one type of model almost by construction of the tool. So the weather atome is done with one model. Ideally, it would be necessary to do this with several atmospheric models just to sample the way the atmospheric circulation is represented, of course. So this analysis comes with a caveat too. But if we are satisfied with the features of the atmospheric circulation, this could go. If we are not, then this might not be good enough.
Thank you so much.
Thanks, Pascal. Pedro, is it okay?
For me?
It's okay, thank you.
Okay, so maybe we have, I have to leave, sorry, but we have a second question by Xenia and a final one by Nicholas. Maybe if you still have time, Pascal, maybe you can carry on. I won't moderate anymore. I have to leave, sorry about this. And thanks to everyone for the relevant questions, okay? And thanks,
Hervé.
Pascal.
Thank you very much.
Okay. Alvaro, if you want to carry on the sharing, maybe if needed.
Okay.
Okay. And thanks, Pascal.
Thank you.
Thank you. Take care.
Just go ahead. Who is the next question? Sorry.
Chinja.
Okay, thank you. So my question is still about the observations. From my understanding that you say you use this observation to constrain your model simulation. So the function of this observation is just to constrain the model, constrain the simulation. So is it that correct that you compare the different model results of the under the different scenarios? For example, your model result is from the different scenario simulations, and then you compare these results. But do you compare the model results with the observations? For example, if it's the distribution of the observation and compare the model and the observation?
Okay, it's not clear. It's not clear that I understand the question, but those models are general climate models. They are not constrained by observations. The only constraint is the initial condition, but the simulations themselves are not constrained by any type of observation. So, among the factual simulations, there are simulations for which there is no precipitation extreme. So some of them do have precipitation extremes. So I realized that the one line is missing on this graph, which is the observation. So the observation of precipitation during January 2014 was around 5.2 millimeters per day. So so that's around this. Okay, so that's on, but the model simulations don't use observations for this. Actually, we could have done this exercise without knowing, because the model simulations are initialized in November, November 2013. With some perturbations in the initial conditions, but that's the case for all simulations. But the meteorology, the atmospheric memory is just a few weeks. So in January, the model has forgotten about what it was in November. Okay, so the only thing that remains is the content in the greenhouse gas concentration. So we simulate a lot of different meteorologies, which sample a lot of the phase space, but most of them are most of the factual are rainier than the counterfactual simulations. I don't know if I'm answering your point. So in the design of the model, those are climate models, general circulation models. They are not constrained by observations, or the way the observations are used are just in a general way. They just verify that some features are respected or some constants. But for the event, we don't use information of the event itself to constrain the model simulations.
Yeah, okay, thank you.
I don't know if there are more questions. If there are no more,
another one.
Sorry, you, Niklas?
Yeah.
Yeah, go ahead.
Okay, so I actually really appreciated the fact, Pascal, that you explained how quickly now attribution studies can be produced. And I experienced also, like after the floodings in Germany, after a couple of days, there was a study like showing how much more probable this event got due to climate change. But I wonder if do you know, does there exist any concentrated effort of the international science community to communicate those results to the more like public society? You just mentioned the website, whether attribution.com, but I mean, this is like putting it out like also like in a science way a bit, but is there, yeah, I mean, because climate change is also like this social and communication challenge, and not only an environmental and physical challenge. And is there any effort internationally to bring this information as concentrated as possible to the governments to highlight those results when they are actually needed by the society?
Yeah, so there are two answers for this. One of them is a national initiative. So there was such an initiative in France, at least, with the Ministry of Environment. to communicate on very simple fact sheets, but I don't know what they are doing with it. So we just produce those sheets, Météo France and IPSL. We give them to the ministry, and because they paid for them, they are supposed to be using rather simple language, avoid jargon. But I don't know. They might be used to take decisions. I don't know. So I don't know what they're doing with this. This is very frustrating for me and for quite a few colleagues in this boat. The other answer, well, Hervé is no longer here, but that's the IPCC. So there's a chapter in the whole chapter in the IPCC on extreme events. Even the summary for policymakers. There's something about the attribution of extreme events, and that would be the most relevant source of information for decision makers. But there are, if you are talking about operational initiatives to transfer the knowledge that we compute, that we obtain in laboratories to either decision makers or stakeholders or companies. That's part of some projects, your research projects, but that's quite a new initiative. I've never seen a clear outcome of this, but this is really work in progress. It's not an obvious thing.
So if there are no questions, Christina was suggesting to take a photo, right, Christina? So just smile and I will take a photo. Or you can also take your own photo, but I will take my photo. Just smile and that's all.
Yeah, but probably the screen should be, the slide should be shared to have all the pictures.
I stop sharing.
Okay, now.
Oh, good idea, Emilio. Thanks. Okay. Last photo. So I think there are no more questions. If you have more questions, please write to Pascal. At some point, he will be able to answer your question, or if not, we will have another session someday of questions and answers. See you tomorrow at 2. Thank you very much, Pascal, and thank you to all of you for your participation.
Thank you.
Thank you, Pascal. See you.
Bye-bye.
Bye. Thank you.
Thanks.
Bye.
Bye.
Thank you.